Tonight we turn our attention to time itself, and specifically to the discovery that time is not the universal, absolute quantity that everyday experience suggests. Time, according to relativity, depends on how fast we move and where we are in a gravitational field. Clocks in different states of motion or at different locations measure different amounts of elapsed time for the same events. This is not speculation or philosophy. It is tested physics, confirmed through countless experiments, and essential for technologies we use daily. We will move through these ideas without excitement or urgency. The relativity of time seems strange because our everyday experience involves speeds and gravitational fields where relativistic effects are negligibly small. But when we extend our observations to fast-moving particles, precise atomic clocks, or satellites orbiting Earth, the effects become measurable and significant. We approach this subject with patience and clarity, building understanding from observations and careful reasoning. Before we can discuss how time behaves in relativity, we need to establish what physicists mean by certain fundamental terms. These concepts involve measurement, reference frames, and the nature of time itself. Time, in physics, is what we measure with clocks. A clock is any device that marks regular intervals. A pendulum swinging, a quartz crystal oscillating, atoms transitioning between energy levels. Time is quantified by counting these regular intervals. A second is defined by a specific number of oscillations of a cesium atom. An hour is 3,600 seconds. We measure time by comparing events to the regular rhythm of a clock. Our everyday experience suggests that time is universal and absolute. If two events happen simultaneously in one place, we assume they happen simultaneously everywhere. If 10 seconds pass on one clock, we assume 10 seconds pass on all clocks, regardless of where they are or how they are moving. This intuition comes from Newton's classical physics, which treated time as an absolute background against which all events occur. In Newtonian physics, time flows uniformly throughout the universe. A clock on Earth, a clock on a moving train, a clock on a distant planet, all measure the same time intervals. The rate of time passage is independent of motion or location. This view worked extraordinarily well for centuries, accurately describing planetary orbits, projectile motion, and countless other phenomena. But it turned out to be an approximation that breaks down when we examine motion at high speeds or gravity at stronger intensities. Reference frames are perspectives from which we make measurements. If you sit in a train, you have one reference frame. Someone standing on the platform has another. The train moves relative to the platform, so measurements of position and velocity differ between the two frames. In classical physics, while positions and velocities differ between frames, time intervals are the same. 10 seconds on the train is 10 seconds on the platform. Relativity changes this. The speed of light is central to understanding time's relativity. Light in vacuum travels at approximately 300,000 kilometers per second. This speed is often denoted by the letter c. In the late 1800s, physicists assumed that light's speed was measured relative to some medium, the luminiferous ether through which light waves propagated. They expected that observers moving through the ether would measure different light speeds depending on their motion. Experiments, particularly the Michelson-Morley experiment in 1887, showed that the speed of light is the same in all directions regardless of Earth's motion. This was puzzling. How could light have the same speed for all observers? If you run toward a light beam, why doesn't it approach you faster? If you run away, why doesn't it recede more slowly? Classical physics could not explain this. Albert Einstein, in 1905, took the constancy of light's speed as a fundamental postulate. If the speed of light is the same for all inertial observers are moving at constant velocity, then something else must change. That something's time and space. Time intervals and spatial distances must depend on the observer's state of motion in such a way that all observers measure the same light speed. This requires abandoning absolute time. Simultaneity is the concept of events happening at the same time. In classical physics, simultaneity is absolute. If two events are simultaneous in one reference frame, they are simultaneous in all reference frames. In relativity, simultaneity is relative. Events that are simultaneous for one observer may not be simultaneous for another observer in motion relative to the first. This relativity of simultaneity follows directly from the constancy of light speed. Proper time is the time measured by a clock moving along a particular path through space-time. It is the time experienced by an observer or object following that path. Proper time is an invariant quantity. All observers agree on the proper time along a given world line, even though they may disagree on coordinate times. A clock moving with an object always measures the proper time for that object. Coordinate time is the time assigned by an observer in a particular reference frame. Different observers in different frames assign different coordinate times to events. But all observers can agree on proper times once they account for their relative motion. This distinction between proper time and coordinate time is essential for understanding time dilation. The Lorentz factor is a mathematical quantity that appears in special relativity. It depends on velocity and becomes significantly greater than 1 as velocity approaches the speed of light. Time dilation, length contraction, and other relativistic effects are proportional to the Lorentz factor. At everyday speeds, the Lorentz factor is negligibly close to 1, so relativistic effects are undetectable. At 90% of light speed, the Lorentz factor is about 2.3, meaning significant time dilation occurs. These definitions form the conceptual foundation. Time is measured by clocks. Light speed is constant for all observers. This constancy requires time to be relative rather than absolute. Different observers in different reference frames measure different time intervals between events. Proper time is invariant, but coordinate time depends on the frame. These ideas, initially counterintuitive, are necessary to reconcile the constancy of light speed with our understanding of motion and measurement. To understand how the relativity of time was discovered and became accepted science, We must trace the development of ideas from classical physics through Einstein's insights to experimental confirmations. In Newtonian physics, formulated in the 17th century, time was absolute. Newton wrote of a true time that flows equably without relation to anything external. This absolute time was universal. The same time coordinate applied everywhere in the universe, independent of motion or observation. Time was a backdrop against which physical events unfolded, distinct from space and independent of the observer. This framework worked extraordinarily well. Newton's laws explained planetary motion, tides, projectile trajectories, and countless phenomena. For more than 2 centuries, Newtonian physics reigned as the accurate description of nature, but subtle problems emerged as experimental techniques improved. The nature of light posed challenges. In the 19th century, James Clerk Maxwell developed equations describing electricity, magnetism, and light as electromagnetic waves. The equations predicted that light travels at a specific speed determined by electrical and magnetic constants. But the equations did not reference any particular observer or reference frame, relative to what did light travel at this speed. Physicists assumed light waves required a medium, just as sound waves require air or water. They proposed the luminiferous ether, an invisible substance filling all space through which light propagated. Light speed would be measured relative to the ether. Earth, moving through the ether, should experience an ether wind that would affect the measured speed of light in different directions. Albert Michelson and Edward Morley designed an interferometer experiment to detect this ether wind. They split a light beam, sent the parts along perpendicular paths, and recombined them. If Earth moved through the ether, light should take different times along the 2 paths, causing an observable interference pattern. The experiment, performed in 1887 and repeated many times, detected no ether wind. Light's speed appeared the same in all directions, yet regardless of Earth's motion. Various explanations were proposed to preserve the ether concept. Perhaps the ether was dragged along with Earth. Perhaps objects contracted in the direction of motion through the ether just enough to hide the effect. These explanations became increasingly contrived. The puzzle resisted resolution within the classical framework. Albert Einstein approached the problem differently. In his 1905 paper on special relativity, he elevated the constancy of light speed to a postulate. Light speed is the same for all inertial observers, not relative to any medium, but as a fundamental property of space-time. He also postulated that the laws of physics are the same in all inertial reference frames. From these 2 postulates, he derived the mathematics of special relativity. The consequences were radical. Time intervals are not absolute, but depend on relative motion. Moving clocks run slow relative to stationary clocks. Simultaneity is relative. Events simultaneous in one frame are not simultaneous in another. Space and time are interwoven into a 4-dimensional spacetime. These results contradicted intuition, but followed necessarily from the postulates. Initial reactions were mixed. Some physicists recognized the elegance and inevitability of Einstein's reasoning. Others found the conclusions too strange to accept. Time dilation and relativity of simultaneity seem to violate common sense. How could time itself depend on motion? But the mathematics was consistent, and the theory made testable predictions. Early experimental support came from observations of particle decay. Unstable particles created by cosmic rays in the upper atmosphere have short lifetimes when at rest, but when moving at speeds close to light speed, they survive much longer from the perspective of an observer on Earth. This extended lifetime is explained by time dilation. The particle's internal clock runs slow relative to Earth's frame. Measurements of muon decay rates matched predictions from special relativity precisely. In 1915, Einstein extended relativity to include gravity with his general theory of relativity. General relativity describes gravity not as a force, but as the curvature of space-time caused by mass and energy. A key prediction is gravitational time dilation. Clocks in stronger gravitational fields run slower than clocks in weaker fields. This effect is distinct from velocity time dilation, but arises from the same underlying framework of spacetime. The first precise test of gravitational time dilation came in 1959 with the Pound-Rebka experiment. Robert Pound and Glenn Rebka measured the gravitational redshift of gamma rays traveling up a tower at Harvard University. Photons climbing 22.5 meters against Earth's gravity lose energy, which manifests as a shift to longer wavelengths. The measured shift matched general relativity's prediction to within 1%. In 1971, Joseph Haffel and Richard Keating performed a more dramatic test. They flew atomic clocks around the world on commercial aircraft, both eastward and westward, and compared them with clocks that remained on the ground. Both velocity time dilation due to the aircraft's motion and gravitational time dilation due to higher altitude affected the airborne clocks. The predictions from relativity, accounting for both effects, matched the measured time differences to within experimental uncertainty. GPS satellites provided an even more stringent test. GPS relies on precise timing. Position is determined by measuring the travel time of radio signals from satellites. The satellites orbit at about 20,000 kilometers altitude, moving at speeds of about 14,000 kilometers per hour. Both gravitational time dilation, weaker gravity, at higher altitude makes satellite clocks run fast, and velocity time dilation, motion makes them run slow, affect the satellite clocks. The net effect is that satellite clocks gain about 38 microseconds per day compared to ground clocks. If these relativistic corrections were not applied, GPS positions would drift by kilometers per day. The system works because engineers include relativistic corrections in the satellite software. Every time you use GPS, you are relying on general relativity's predictions about time dilation. The success of GPS is a daily, practical confirmation that time is relative. Modern experiments with atomic clocks have reached extraordinary precision. Clocks accurate to 1 part in 10 to the 18th can detect time dilation over height differences of a single centimeter. Experiments have measured gravitational time dilation by comparing clocks separated vertically by just 33 centimeters. The effects are tiny at such small scales, but measurable with sufficiently precise clocks. These experiments continue to confirm general relativity with increasing accuracy. The history shows how scientific understanding evolves. Classical physics assumed absolute time because relativistic effects were too small to detect with available instruments. As measurement precision improved and observations extended to high speeds and precise clocks, the inadequacy of absolute time became apparent. Relativity replaced absolute time with a framework where time depends on motion and gravity. Experimental confirmations accumulated, and relativity became established physics. Time's relativity is now tested routinely in particle accelerators, GPS satellites, and precision laboratories. Time dilation refers to the phenomenon where clocks in different states of motion or different gravitational fields measure different elapsed times. Understanding time dilation requires careful explanation of how it arises and what it means. Velocity time dilation is the effect where a moving clock runs slower than a stationary clock. This is a consequence of special relativity and the constancy of light speed. To see why, consider a simple thought experiment involving a light clock. A light clock consists of two mirrors separated by a distance, with a pulse of light bouncing back and forth between them. Each round trip is one tick of the clock. Imagine this light clock is at rest in your reference frame. The light travels straight up and down between the mirrors. The time for one tick is the distance between mirrors divided by the speed of light. This is straightforward. Now imagine the light clock is moving sideways relative to you, carried on a fast-moving spacecraft. You still observe the light bouncing between the mirrors, but from your perspective, the light follows a diagonal path. It moves sideways with the clock, while also moving up and down between the mirrors. The diagonal path is longer than the straight vertical path. Since the speed of light is the same for you and for an observer on the spacecraft, and the light travels a longer path from your perspective, more time must pass in your frame for one tick of the moving clock. The moving clock ticks more slowly from your perspective. This is time dilation. The moving clock runs slow relative to the stationary clock. This reasoning applies to all clocks, not just light clocks. Any process that marks time, atomic transitions, pendulum swings, biological aging, slows down when moving relative to an observer. Time itself, in the moving frame, passes more slowly from the stationary observer's perspective. This is not a mechanical effect specific to how clocks are built. It is a property of time. The amount of time dilation depends on velocity through the Lorentz factor. At low speeds compared to light speed, time dilation is negligible. At 10% of light speed, the Lorentz factor is about 1.005, meaning clocks slow by about 0.5%. At 50% of light speed, the factor is about 1.15, and clocks slow by about 15%. At 90% of light speed, the factor is about 2.3, and moving clocks tick at less than half the rate of stationary clocks. An important subtlety is that time dilation is reciprocal. If you observe a spacecraft moving past you, you see clocks on the spacecraft running slow. But from the perspective of someone on the spacecraft, they are at rest. And you are moving. They see your clocks running slow. This seems paradoxical. How can each observer see the other's clocks running slow? The resolution is that time dilation is real for each observer's measurements, and there is no contradiction because simultaneity is relative. Events that are simultaneous in your frame are not simultaneous in the spacecraft's frame. The twin paradox illustrates this subtlety and its resolution. Imagine two twins, one staying on Earth and one travelling to a distant star and returning. During the journey, each twin sees the other's clock running slow due to relative motion. But when they reunite, the travelling twin has aged less than the Earth twin. The asymmetry arises because the travelling twin accelerated, changed velocity to turn around and return. Acceleration breaks the symmetry between the two reference frames. The travelling twin's world line through space-time is different from the Earth twin's world line. The proper time along the travelling twin's path is less. This is not a paradox, but a consistent prediction of relativity, confirmed by experiments. Muons provide a clear, real-world example of time dilation. Muons are unstable particles created when cosmic rays collide with atoms in Earth's upper atmosphere, about 15 kilometers high. A muon at rest has an average lifetime of about 2 microseconds before decaying. Even travelling at 99% of light speed, a muon would travel less than 1 kilometer in 2 microseconds. Classical physics predicts that muons should decay long before reaching Earth's surface. Yet muons are detected at sea level in large numbers. The explanation is time dilation. From Earth's reference frame, the fast-moving muons' internal clocks run slow. Their 2 microsecond lifetime is extended by the Lorentz factor. At 99% of light speed, the factor is about 7. So the muons live about 14 microseconds in Earth's frame, allowing them to travel 15 kilometers and reach the surface. From the muon's reference frame, its lifetime is still 2 microseconds by its own clock. But in the muon's frame, Earth is rushing toward it at 99% of light speed, and the atmosphere is length contracted. The 15 kilometers of atmosphere is contracted to about 2 kilometers in the muon's frame. The muon travels 2 kilometers in 2 microseconds, reaching the surface. Both perspectives are consistent. Time dilation in Earth's frame corresponds to length contraction in the muon's frame. Particle accelerators routinely observe time dilation. Unstable particles created in collisions live longer when moving at high speeds, exactly as relativity predicts. The Large Hadron Collider accelerates protons to 99.99999% of light speed. At these speeds, the Lorentz factor is about 7,000, and time dilation is enormous. Particles that would decay almost instantly at rest survive long enough to circle the entire accelerator ring multiple times for decaying. Astronauts in low Earth orbit experience time dilation, though the effect is tiny. The International Space Station orbits at about 7.7 kilometers per second. At this speed, velocity time dilation causes clocks on the station to run slow by about 27 microseconds per day compared to Earth's surface. However, the station is also at a higher altitude where gravity is slightly weaker. So gravitational time dilation causes clocks to run fast by about 52 microseconds per day. The net effect is that astronauts age about 25 microseconds per day, more than people on Earth's surface. Time dilation is not a trick of perception or signal delay. It is a real difference in elapsed time measured by accurate clocks. When a moving clock returns to rest beside a stationary clock, less time has passed on the moving clock. This has been measured directly in Hafele-Keating experiments and countless other tests. The moving clock genuinely experienced less time. Time itself passed more slowly in the moving frame. Understanding velocity time dilation requires accepting that time is not absolute. The rate of time passage depends on motion. This contradicts everyday intuition because everyday speeds are tiny compared to light speed, but careful measurements at high speeds or with precise clocks reveal the effect consistently. Time dilation is not speculative. It is observed physics, essential for understanding high-energy particles, for operating GPS satellites, and for reconciling the constancy of light speed with measurements made in different reference frames. Gravitational time dilation is the phenomenon where clocks in stronger gravitational fields run slower than clocks in weaker fields. This effect arises from general relativity's description of gravity as the curvature of spacetime. In general relativity, mass and energy curve spacetime. This curvature affects both the paths objects follow, what we perceive as gravitational attraction, and the passage of time. Regions of stronger gravitational field, deeper in space-time's curvature, experience slower time compared to regions of weaker field. This is gravitational time dilation. The effect can be understood qualitatively through the equivalence principle, which states that gravity and acceleration are locally indistinguishable. Imagine a rocket accelerating in deep space, far from any gravitational fields. Inside the rocket, an observer feels a force pushing them toward the floor, indistinguishable from gravity. Light emitted from the floor towards the ceiling's Doppler shifted toward lower frequencies, redshifted, because the ceiling accelerates away from the light. By the equivalence principle, light climbing in a gravitational field should also be redshifted. Since frequency and energy are related, the light loses energy climbing against gravity. For light to be redshifted in a gravitational field, time must run at different rates at different heights. A clock lower in the field emits light at a certain frequency. That light, climbing to a higher altitude and observed by a clock there, is redshifted, observed at a lower frequency. The only way this can happen consistently is if the lower clock's ticking slower than the higher clock. Time passes more slowly, deeper in the gravitational field. The Pound-Rebka experiment in 1959 measured gravitational redshift directly. Gamma rays were emitted from an iron source at the bottom of a tower and detected at the top 22.5 meters higher. The gamma rays lost energy climbing against Earth's gravity, manifesting as a shift in frequency. The fractional change in frequency was about 2.5 parts in 10 to the 15th, extraordinarily small. But using the Mossbauer effect, which allows precise measurement of gamma ray frequencies, Pound and Rebka detected the shift and found it matched general relativity's prediction. This experiment confirmed that time runs at different rates at different gravitational potentials. A clock at the bottom of the tower ticks slightly slower than a clock at the top. The difference is minuscule, about 2 nanoseconds per day for a height difference of 22 meters on Earth. But it is measurable and real. Atomic clocks flown at different altitudes show gravitational time dilation directly. In the Hafele-Keating experiment, atomic clocks were flown on commercial aircraft around the world and compared with clocks on the ground. The airborne clocks experienced both velocity time dilation due to motion and gravitational time dilation due to altitude. At cruising altitude, gravitational time dilation caused clocks to gain about 53 nanoseconds per day, partially offsetting the 32 nanoseconds per day lost to velocity time dilation. The net prediction, accounting for both effects and the complex paths flown, matched the measured differences. Modern atomic clocks can detect gravitational time dilation over centimeter scale height differences. Experiments at NIST have compared clocks separated vertically by 33 centimeters and measured the predicted time difference. At this separation, gravitational time dilation causes clocks to differ by about 4 parts in 10 to the 18th, a few 10,000ths of a nanosecond per day. The clocks are accurate enough to measure this. Such experiments test general relativity at unprecedented precision and also raise the possibility of using atomic clocks as exquisitely sensitive altitude sensors. GPS satellites experience significant gravitational time dilation. At an orbital altitude of about 20,000 kilometers, Earth's gravitational field is weaker than at the surface. General relativity predicts that satellite clocks run faster than ground clocks by about 45 microseconds per day due to this weaker gravity. Combined with the velocity time dilation effect of about 7 microseconds per day slower, clocks slow because satellites are moving, the net effect is that satellite clocks gain about 38 microseconds per day. Engineers adjust the satellite clocks before launch, setting them to tick slightly slow so that once in orbit, relativistic effects bring them into synchronization with ground clocks. If these corrections were not made, GPS would quickly become inaccurate. Position errors would accumulate at about 10 kilometers per day. The practical necessity of these corrections demonstrates that gravitational time dilation is real and significant even for Earth's relatively weak gravity. Near more massive objects, gravitational time dilation becomes more pronounced. At the surface of the Sun, gravity is about 28 times stronger than at Earth's surface. Clocks there run slow by about 2 parts in a million compared to clocks far from the Sun. This gravitational redshift of light from the Sun has been measured and matches general relativity's predictions. White dwarf stars remnants of stars like the Sun are much denser. At the surface of a typical white dwarf, gravity is hundreds of thousands of times stronger than at Earth's surface. Gravitational time dilation causes clocks there to run slow by about 1 part in 10,000. Light from white dwarfs is gravitationally redshifted, and this has been observed and measured, confirming the predicted time dilation. Neutron stars, even denser than white dwarfs, have gravity so strong that gravitational time dilation is a significant fraction. At a neutron star's surface, clocks might run 20 to 30% slower than clocks far away. Light from neutron stars is significantly redshifted. These extreme time dilation effects are consistent with general relativity's predictions, though measuring them precisely is challenging due to the complexities of neutron star atmospheres and magnetic fields. Near a black hole's event horizon, gravitational time dilation becomes extreme. As an object falls toward the event horizon, time dilation increases without bond from the perspective of a distant observer. The falling object appears to slow down asymptotically, its light redshifted to longer and longer wavelengths, eventually becoming undetectable. From the falling object's perspective, proper time continues normally, and the horizon is crossed in finite time. But to an outside observer, the object never quite reaches the horizon, frozen by infinite time dilation. Gravitational time dilation is distinct from velocity time dilation, though both are aspects of general relativity's unified description of spacetime. Velocity time dilation is reciprocal. Each of two observers in relative motion sees the other's clock slow. Gravitational time dilation is not reciprocal in the same way. A clock deeper in a gravitational field unambiguously runs slower than a clock higher up. All observers agree on this, regardless of their own motion. The difference arises because gravitational time dilation involves space-time curvature, while velocity time dilation involves relative motion through flat or nearly flat space-time. The mathematical description involves the metric of spacetime, which specifies how distances and times are measured. In curved spacetime near a massive object, the metric depends on position. The rate of time passage varies with gravitational potential. Clocks at different potentials measure different proper times along their world lines, even if they remain stationary in space. Gravitational time dilation has been tested in many contexts and always confirmed, from laboratory experiments measuring redshift over meters to GPS satellites compensating for altitude effects to observations of light from massive stars. The predictions of general relativity match observations. Time genuinely passes at different rates in different gravitational fields. This is not philosophy or interpretation. It is measured, confirmed physics, essential for accurate timekeeping and navigation. Time dilation is not merely theoretical. It appears in practical applications and has been measured in numerous experiments. Examining specific examples helps make the concepts concrete and demonstrates the reality of time's relativity. GPS satellites provide the most widespread practical application of relativistic time dilation. The global positioning system consists of satellites orbiting the Earth at about 20,000 kilometers altitude, each carrying atomic clocks. Position on Earth is determined by receiving signals from multiple satellites and calculating the distance to each based on signal travel time. Accurate timing is essential. An error of 1 microsecond translates to a position error of about 300 meters. The satellites orbit at about 14,000 kilometers per hour. At this velocity, special relativity predicts that satellite clocks run slow by about 7 microseconds per day compared to clocks at rest on Earth's surface. But the satellites are also at higher altitude where Earth's gravitational field is weaker. General relativity predicts that clocks in weaker gravity run faster. At GPS orbital altitude, gravitational time dilation causes clocks to run fast by about 45 microseconds per day compared to ground clocks. The two effects partially cancel, but the gravitational effect is larger. The net result is that satellite clocks, if not corrected, would run fast by about 38 microseconds per day compared to ground clocks. Over a single day, this would cause position errors of about 11 kilometers. Within a week, GPS would be essentially useless. Engineers account for these effects by adjusting the satellite clocks before launch. The clocks are set to tick at a rate slightly different from ground clocks, so that once in orbit, with both velocity and gravitational time dilation acting, they synchronize with ground time. This adjustment is permanent, built into the satellite's design. Every GPS receiver you use benefits from corrections based on general relativity. The system's success is a daily, practical confirmation of time dilation. Particle physics experiments routinely observe time dilation of fast-moving particles. Muons, as mentioned earlier, are created in the upper atmosphere by cosmic rays. With a rest lifetime of about 2 microseconds, classical physics predicts they should decay before reaching sea level. Yet they are detected at Earth's surface because time dilation extends their lifetime from the ground observer's perspective. Measurements of muon flux at different altitudes match the predictions of special relativity precisely. In particle accelerators, unstable particles are accelerated to speeds extremely close to light speed. Pions, for instance, have a rest lifetime of about 26 nanoseconds. At the Large Hadron Collider, where particles move at 99.99999% of light speed, the Lorentz factor can exceed 10,000. Pions live 10,000 times longer in the lab frame than they would at rest, allowing them to travel meters or even kilometers before decaying. Without time dilation, these particles would decay essentially at the point of creation. The fact that they travel measurable distances confirms that time dilation is real and matches predictions. Atomic clocks in precision tests have demonstrated time dilation at remarkably small scales. In experiments at the National Institute of Standards and Technology, NIST, optical atomic clocks, the most precise timekeepers ever built, have been compared at different heights. Clocks separated by just 33 centimeters show measurable gravitational time dilation. The effect is about 4 parts in 10 to the 18th, equivalent to clocks differing by about 1 second over the age of the universe. Yet the clocks are precise enough to measure this difference over much shorter timescales. Other NIST experiments have measured velocity time dilation at low speeds. Clocks on slowly rotating platforms show the predicted time dilation compared to stationary clocks. The effect is tiny. Rotating at a few kilometers per hour produces time dilation of only about 10 to the negative 16th, but measurable with the best atomic clocks. These experiments confirm that time dilation occurs even at everyday speeds, though it is far too small to notice without extraordinarily precise instruments. Gravitational redshift from the Sun was measured as early as the 1920s, though with limited precision. Light emitted from the Sun's surface must climb out of the Sun's gravitational well. Photons lose energy in the process, manifesting as a shift to longer wavelengths. The fractional wavelength shift is about 2 parts in a million. Early measurements were complicated by other effects like the Doppler shift from the Sun's rotation and convective motions in the solar atmosphere, but by carefully accounting for these, the gravitational redshift was confirmed. More precise measurements came from observations of white dwarf stars. Sirius B, the white dwarf companion to Sirius, has strong enough gravity that its gravitational redshift is about 30 parts in a million. This shift has been measured and matches general relativity's prediction. Similar measurements for other white dwarfs provide additional confirmation. Time dilation near Earth has been measured with atomic clocks flown on aircraft, as in the Hafele-Keating experiment. Clocks flown eastward around the world, travelling in the direction of Earth's rotation, moved faster relative to the centre of the Earth and experienced more velocity time dilation. They lost time compared to ground clocks. Clocks flown westward, travelling against Earth's rotation, moved slower relative to Earth's centre and experienced less velocity time dilation. They gained time. Both also experienced gravitational time dilation from higher altitude. The predicted and measured time differences agreed within experimental uncertainty, confirming both velocity and gravitational time dilation. Modern versions of this experiment use commercial flights and portable atomic clocks. Results consistently confirm relativistic predictions. The effects are small, tens of nanoseconds for a transcontinental flight, but clearly measurable. Time dilation even affects electrons in atoms. Electrons in heavy atoms move at significant fractions of light speed in their orbitals. The innermost electrons in gold atoms, for example, orbit at speeds approaching 60% of light speed. Relativistic effects, including time dilation, affect these electrons' energies and the atom's properties. Gold's characteristic yellow color arises partly from relativistic effects, shifting electron energy levels. Without relativity, we would not correctly predict gold's color or many other properties of heavy elements. These examples span a wide range: GPS satellites, cosmic ray muons, particle accelerators, atomic clocks on aircraft and in laboratories, gravitational redshift from massive stars, and even atomic structure. In every case, observations match the predictions of relativity. Time dilation is not confined to exotic conditions. It affects particles, satellites, light, and atoms. It is measured routinely and incorporated into technology. The consistency and ubiquity of confirmations demonstrate that time's relativity is established physics, not speculation. Time's relativity connects to many areas of physics and shapes our understanding of space-time, the universe, and the fundamental nature of reality. General relativity provides the complete framework for understanding time dilation. Special relativity describes time dilation due to relative velocity in flat space-time. General relativity extends this to include gravity, describing it as space-time curvature. In general relativity, mass and energy curve space-time, and this curvature affects both motion and time. Gravitational time dilation arises naturally from the curved geometry near massive objects. The mathematics involves the metric tensor, which specifies distances and times in curved space-time. The metric depends on the distribution of mass and energy. Solving Einstein's field equations gives the metric for various situations around a spherical mass like Earth near a rotating black hole in an expanding universe. From the metric, we can calculate how much proper time elapses along different paths through space-time. Space-time is the unified four-dimensional structure combining space and time. In classical physics, space and time are separate. In relativity, they are interwoven. An event is a point in space-time, specified by 3 spatial coordinates and 1 time coordinate. The separation between events is described by the space-time interval, which combines spatial distance and time difference. The space-time interval is invariant. All observers agree on it, even though they may disagree on the separate spatial and temporal components. Time is often called the 4th dimension, but it is not quite like the spatial dimensions. The space-time interval has a different sign for time than for space, reflecting the fundamental difference between time-like and space-like directions. You can move freely in spatial directions, but only forward in time. Despite this difference, space and time are mixed by relative motion. What one observer considers purely spatial separation, another in relative motion sees as having a temporal component. This mixing of space and time is central to relativity. Cosmology relies on general relativity to describe the universe's large-scale structure and evolution. In cosmological models, there is a notion of cosmic time, a time coordinate natural to observers moving with the overall expansion of the universe. This cosmic time provides a universal clock for describing the universe's history. But even cosmic time is not absolute. Observers in different gravitational fields or with different velocities measure different proper times. Cosmology uses general relativity's framework, including time dilation, to interpret observations of distant galaxies and the cosmic microwave background. Black holes represent extreme time dilation. Near a black hole's event horizon, space-time curvature becomes so severe that time dilation approaches infinity from the perspective of a distant observer. An object falling toward the horizon appears to slow down asymptotically, never quite crossing. Light from the object is redshifted toward an infinite wavelength. Yet from the falling object's perspective, proper time continues, and the horizon is crossed in finite time. This mismatch between perspectives is resolved by careful analysis of different reference frames. Inside the event horizon, the roles of space and time change. The direction toward the singularity becomes time-like. It is the direction toward the future, unavoidable, like time's forward march. This strange behavior arises from the extreme curvature of space-time. Understanding black holes requires understanding time's behavior in highly curved space-time. Thermodynamics and their area of time raise questions about time's direction. Unlike water relativity, which treats past and future symmetrically in its equations, thermodynamics distinguishes a direction. Entropy increases with time. This thermodynamic arrow gives time an orientation from past to future. Why time has this arrow and how it relates to the initial conditions of the universe remains an area of research. Relativity describes how time is measured and how it varies with motion and gravity, but it does not explain why time flows in one direction. Quantum mechanics and time have a complex relationship. In quantum mechanics, time is treated as a parameter, not an observable like position or momentum. There is no time operator in standard quantum theory. The measurement problem in quantum mechanics concerns when and how wave function collapse occurs, which involves the progression of time. Reconciling quantum mechanics' treatment of time with general relativity's dynamic, curved time remains a challenge in developing a quantum theory of gravity. Philosophy of time addresses questions about time's nature. Does it flow, or is that an illusion? Is the present special, or are past, future, and present equally real? Physics, including relativity, informs these questions, but does not answer them definitively. Relativity shows that simultaneity is relative and that time is intertwined with space, but it does not resolve all philosophical puzzles about time's nature. The connections between time, space-time, gravity, cosmology, thermodynamics, and quantum mechanics illustrate time's centrality to physics. Time is not a simple background parameter. It is dynamic, relative, and interwoven with the structure of space-time. Understanding time requires understanding general relativity, and understanding general relativity requires appreciating time's relativity. These connections continue to guide research at the frontiers of physics. As we move toward the close of our discussion, we can restate gently some of the central ideas we have explored. Time is not absolute, but relative. The rate at which time passes depends on how fast we move and where we are in a gravitational field. This is not speculation or philosophy, but established physics, confirmed through countless experiments and essential for technologies like GPS. Velocity time dilation occurs because the speed of light is constant for all observers. When one observer moves relative to another, each sees the other's clock running slow. This reciprocal slowing is real, not an illusion. When clocks reunite, less time has genuinely passed on a clock that moved than on one that remained stationary. The twin paradox illustrates this. A travelling twin ages less than a stay-at-home twin because acceleration breaks the symmetry between their world lines. Muons created in the upper atmosphere survive to reach Earth's surface because time dilation extends their lifetimes from the ground observer's perspective. Particles in accelerators live far longer than they would at rest. These observations match special relativity's predictions precisely. Time dilation is observed routinely in particle physics. Gravitational time dilation occurs because mass curves spacetime. Clocks deeper in a gravitational field run slower than clocks higher up. This has been measured in the laboratory over height differences of centimeters. Clocks on GPS satellites run faster due to weaker gravity at altitude, requiring corrections to maintain system accuracy. Gravitational redshift of light from the Sun and white dwarf stars confirms that time passes at different rates in different gravitational fields. The two types of time dilation, velocity and gravitational, are unified in general relativity's description of spacetime. Spacetime is curved by mass and energy, and this curvature affects both the paths objects follow and the passage of time. Time and space are interwoven into a four-dimensional structure. Measurements of time and space depend on the observer's motion and location in curved spacetime. GPS satellites experience both types of time dilation. Velocity time dilation slows their clocks by about 7 microseconds per day. Gravitational time dilation speeds their clocks by about 45 microseconds per day. The net effect is that satellite clocks gain about 38 microseconds per day. Engineers compensate by adjusting the clocks before launch. Without these relativistic corrections, GPS would fail. Atomic clocks provide precision tests of time dilation. Modern clocks can measure gravitational time dilation over height differences of centimeters and velocity time dilation at speeds of kilometers per hour. Every test confirms general relativity's predictions. The consistency across many experiments using different methods in different contexts builds overwhelming evidence. Time's relativity seems counterintuitive because everyday speeds and gravitational fields produce negligible effects. We do not notice time dilation in daily life, but at high speeds approaching light speed or with precise enough clocks, the effects become measurable and significant. The universe operates according to relativistic physics, even if our intuition, built from everyday experience, does not expect it. The constancy of light speed requires time to be relative. If light travels at the same speed for all observers, then observers in relative motion must measure different time intervals for the same events. Simultaneity becomes relative. Events simultaneous in one frame are not simultaneous in another. These consequences follow necessarily from the constancy of light speed. General relativity extends special relativity to include gravity and acceleration. It describes gravity as space-time curvature, rather than a force. Massive objects curve the space-time around them, affecting both motion and time. Clocks near massive objects run slower. Light climbing out of gravitational wells is redshifted. These effects are predicted by general relativity and confirmed by observation. Time dilation is not merely a theoretical curiosity. It affects satellites, particles, light, atoms, and any system where precise timing matters. It has been tested in laboratories, in particle accelerators, in Earth orbit, and through astronomical observations. The theory's predictions match observations to extraordinary precision. Time's relativity is as well established as any result in physics. We have moved through these ideas slowly, building understanding from observations and careful reasoning. The concepts are subtle, involving the interplay of motion, gravity, and the structure of space-time. But they are grounded in measurements and confirmed through diverse experiments. Time's relativity is real, tested, and essential for understanding the universe. We have now travelled through the essential concepts of time's relativity, how time depends on motion through velocity, time dilation, how it depends on gravity through gravitational time dilation, and how both effects are unified in general relativity's description of curved space-time. We have seen how these predictions are confirmed through experiments ranging from particle physics to GPS satellites to precision atomic clocks. There is no need to retain every detail. Time's relativity involves ideas that seem strange at first because they differ from everyday experience. Understanding develops gradually through reflection on the evidence and careful thinking about what measurements reveal. You may have drifted in and out as we spoke, and that is entirely natural. Each section we discussed was intended to stand on its own, so that wherever your attention rested, you encountered ideas that were complete in themselves. Time, we have discovered, is not the universal backdrop that Newton imagined. It is dynamic, interwoven with space into space-time, and relative to the observer's motion and gravitational field. Clocks in different circumstances measure different amounts of time. These effects are measured and real. They shape the universe and influence technologies we use daily. We close gently, without urgency, as we began. The concepts we explored are supported by extensive experimental evidence and grounded in the well-tested framework of general relativity. Time's relativity is one of the great insights of modern physics, revealing that the universe is stranger and more subtle than everyday intuition suggests. These ideas will remain where they are, available for reflection should you wish to return to them. Rest now if you wish. There is nothing more required of you tonight.